Hey everyone, so this is our first ever video and today we will be seeing gradient descent. So first of all, what is gradient descent? So let's say we have a graph like this, a bell-shaped curve, please excuse my drawing, something like this. So when we initialize our neural network, we may be randomly initialize anywhere based on our weight and biases. Now, the main motive of the neural network is to reduce the loss function, however possible. So how can we do that? And what is the loss function? So the loss function, it can be anything. Let's take it as the difference of the y minus the y expected, y the actual y minus the y that we predicted whole to the power square. So this is one of the loss function. This is the most basic one actually. So let's take it as our loss function. So our main motive is to reduce this loss function. And what this graph is showing is the graph between our loss function, the graph between our loss, eh, sorry, I'm a little confused. So what is it? Is the graph between our loss function mm, so on the y-axis we have our loss function and on the x-axis we have our values. Pretty easy. Now, what is our main goal? Our main motive is to reduce the loss function any way possible. And how will we do that? First of all, our target will be to go to the direction where the loss function is minimum. And that is where gradient descent comes into play. Let's say we have a function. Let's say we have a linear function y equals to mx plus c. Now, c is our bias and m is our weight according to machine learning terms here. So what we need to do, we need to find the value of m and c in such a way that our loss is minimum for this formula. So what can we do? First of all, we will get the derivative of this. We will get dy by dm, keeping the c constant, c equals to constant, and we will also get dy by dc m constant for this loss function, and this will help us to find the direction. Like in this case of this point, we can see the direction we should be moving into is this. So how the direction in which we need to move is decided by the gradient. Now how much should we move in this direction is decided by our learning rate. If we move too much in this direction, we may overshoot. We may overshoot our destination, that is this global minimum, and we may go to the other side of the point. But we don't want that. We want that we don't overshoot and slowly maybe we go to this in the next step. Then in the second step we go a little more. Then in the third step we finally reach our global minimum. And that is our final target here. So in order to achieve that target, we need to have two main things. One is the loss function and the second is the direction of the gradient. Now today we will be applying these two things in a very basic way in a linear regression problem. So what is linear regression? Let me show you. Let's say we have points. This is random enough. Let's say we have points. Let's make them little linear and few outliers. So linear regression finds the line of best fit for this point. So this is the line of linear regression. So for any given x, for any given x, let's change the color too for this. For any given x, we will find a given y. We will have a given y, and this is what our linear regression does. For any given x, it plots the x on the line of best fit and gives us the value of our point. Now, how will we use gradient descent in linear regression? So this curve, this linear line has an equation. Maybe that is, let's say that is what? A linear equation. What is linear equation? Y equals to mx plus c. Looks pretty similar, right? Looks pretty similar to what I have told before, this one. This one. Now, what is our x? Our x here, what is our m? The m here is the weight and the c here is the bias for our model. Now, now that we have understood little theory behind what we are going to do, let's move on and actually do it. Okay, then I have this notebook written. Let me clear all the outputs and restart the terminal, and then we will be starting from the beginning. So let me first introduce to our data set. This is our data set. We have the date, we have the maximum temperature of today, the minimum temperature of today, the date, the amount of rain, and the variable we need to predict is tomorrow's maximum temperature. So let's first, I will line by line explain and execute every cell. So what our first cell is doing is, we are importing pandas as PD, and then we are importing our .csv file using pd.readcsv function into our data frame variable. Next up, we are using df equals to df.fffill, which I will explain in a second. And lastly, we are using df.head to see the first few rows. So let's run this run this cell. So now this is our row. As you can see, date, tmax, tmin, the amount of rain, and the tomorrow's maximum temperature. Now what does df.fffill does? Let's say this 52 was actually a null. So what this function will do is, it will use the previous temperature or the previous value to fill this null row or the null cell. So there is no null value that can interrupt our training procedure later on. So that is the use of df.fffill. So now next what we are doing, after reading data, we are going to our linear regression using sklearn. First we will use sklearn and then we will declare our gradient descent. So we are importing from sklearn.linear model our linear regression class, which holds the linear regressor to train on. Next, we are importing numpy as np, and lastly we are using test and split from sklearn.model selection to split our dataset into test and train. Now we are initializing x equals to df.ilog, colon means all the rows, from column number 1 to the second last, minus 1. The last value is not considered in df.ilog. So from column number 1, that is tmax, to just before minus 1, that is before tmax tomorrow. So tmax to rain, all three columns, tmax, tmin and rain, and y equals to df.ilog all the rows and the negative one or the last column, that is tmax tomorrow. And we are converting our pandas data frame to numpy array, which is better suited for machine learning training. Next, we are breaking up the data into x train, y train, then x validate, y validate, and x test, y test, using the train test fleet from sklearn. And after that, we are declaring an object of the class linear regression, naming it regressor. Then we are fitting that object with our data, regressor.fit x train, y train. Now let's run this cell. It will take a few seconds. So while that cell is running, let us see what we are doing in our next cell. So first we are taking x equals to np.array. Same thing is happening in this much part. Now what here it is happening is, as in the previous cell we have taken all three columns, here we are only taking the first column, that is our tmax for today, and with that only we were training our linear regressor to see the difference. Now we will run this as well. As you can see, both our regressors are trained. Next, we will be seeing the scores of both the regressors. This is the regressor with all the three columns, and this is the regressor with only one column, that is my today's maximum temperature. As you can see, the regressor with all three columns gets a little better score than the regressor with only today's maximum temperature column. Next, we will be seeing the weight and biases of these both. Let's see. So for the multidimensional regressor or regressor with all the three columns, the weights are 0.71, 0.18, and minus 2.69 specifically. And the bias is 9.73. And the weights for our single dimensional regressor, where we are only passing the today's maximum temperature, is 0.81 and the bias is 12.08. Now these are our scores and weights and biases for our regressors. Now we will be calculating our own gradient descent, and we will be seeing how that works. First of all, let us plot all the tmax and the tmax tomorrow using matplotlib.plt. We will use plt.scatter to plot all our tmax and tmax tomorrows, and then we will use our regressor to predict the x value and see. This won't be a very pretty picture because this regressor is actually multi-dimensional, but we are trying to print it into a single dimension. So as you can see, this green line is a regressor. It is not a very good picture as we are using it in a hyperplane. Let me quickly explain what that is. So if you see, if we come back here and let us say this is one, this these are few of my points in a plane, and these are few other points. Now how will I separate these 2 points? Let's think these are all in 3D plane. Okay, this is my x-axis, this is my y-axis, and this is my z-axis. Or this is my x-axis, this is y, and this is my z-axis. Now let's say this is one cluster, this here is one cluster, this here is my second cluster. So how will we linearly separate this in our three-dimensional plane? So in 2D, as we have seen, we draw a line. In 3D, what we do is we draw a hyperplane. Let me see if I can draw this. No. Okay. Let me draw it myself. So what we will do here, we will draw a hyperplane. Imagine this plane is going between this part and this part and separating them. So this is what we draw in 3D. This hyperplane. Now when we plot this hyperplane in a two-dimensional axis, it looks something like this. Okay. So next what we will be doing is we will be declaring our loss function here. So our loss function, as we have seen, is this one, y actual minus y predicted whole square. Okay. So here this is my y actual, w x plus my bias minus my y actual whole to the power squared. This is little wrong. Let me correct this. This will be y actual minus y predicted whole square. So let me run this. And as you can see, let me explain. Now ws is I am taking the weights in the range of -1 to 3 with a step gap of 0.1, and y is 80. As we have seen from this prediction, here y is 0.81, so I am taking 80 and the bias is 12. I am taking 9.56, or I can take 12 also here. If you want, I can take 12 as well. Rerun this. So as you can see, my weight is W in the range -1 to 3 with the step count of 0.1. I am thinking that the Y, or today's maximum temperature, is 80 and the loss is sorry, Y is the tomorrow's maximum temperature. And now I am calculating losses for all these weights, keeping WS and tomorrow's maximum temperature as 80. Now what we need to do is we will PLT.scatter all our weights versus our losses, and we will see how that varies. As you can see, as the weight goes away from the point, for 3 the weight loss is very high, around 25,000. Similarly, as we go away from the point in the negative direction, our weight is also increasing. Now this red point is our current weight, that is when our weight is 1. This I am plotting here when the weight is 1 and the loss for that weight is less. Now as we go down, say that our regressor gave us a weight of 0.81. So if we use that here, see our loss reduced by a little. Our loss can reduce even more, as we can see from the graph. If you shift it little towards the right, our loss will reduce little more. So this is the change of the losses with different weights around our function. Next, we will be seeing similar thing, but this time for our biases. So as our biases change, how our loss is also changing. Let me correct this. And let's run it now. So see, for the bias of 10, this is our loss. And as we change the as we take the range from -30 to 30, our loss increases as we go right or left, and as we come to the middle, our loss reduces. But this, both of this are individual losses, means we are taking the bias as constant at 12, and here we are taking the weight at a constant of 1, as you can see from the formula. But that is not the case actually. Actually both of our biases and our weights perform together, not differently. So with together we will find a common area. So but this is a 2D graph, and if we need to plot all our biases, weights, and our loss function in the same graph, it will become a 3D graph. So I won't be explaining how we are plotting the 3D graph, but we will be having a look at that, and we will be seeing how it looks. So this is our 3D graph, okay? And this star as you can see here is our optimal point in this 3D graph. As you can see, if we plot this, the bias comes around 9 point something or 11 point something here near, and our weight comes around 0.7, 0.8, closer to that range. So together, this is the loss function of both the weight, bias, and our loss together. This is the graph of that. Next, we saw our losses. Now, let us see our gradient. Okay. So now let us see what is our gradient. Now, let us see our gradient function. Gradient equals to lambda w comma y 2 into y minus w into 80 minus 10. So let me explain what this is. As we have seen before, that what is our equation? Our equation is w into x plus our bias. Okay, our equation is w into x plus our bias. Now what is our loss function is? Our loss function is y minus the y predicted whole square. Y minus y predicted whole square. Now what we are doing here is we are first taking derivative of this with respect to the weight. Now if weight is constant, the 2 comes, so it becomes 2 into y minus y predicted, that is y minus, this is the predicted function na? So y minus y predicted multiplied with derivative of this, only this part with respect to w, that is x, that we are multiplying here, this x, because x, what is x? X is the today's maximum temperature that we are taking as 80. Now as we plot this, that is PLT dot scatter ws with our gradient, and like we are taking both tomorrow's maximum temperature and today's maximum temperature as 80. Okay, don't get confused in that. As we plot this PLT dot scatter, and we plot our point with the weight being 1, and what is the gradient for that, we will see a straight line. Yeah, see, this is our straight line. In this straight line, as we go downwards, our gradient loss increases, or as we go upward, our gradient loss increases. So what we need to do is we need to stay at 0. So if we go upward, we reduce the value with the gradient. If our weight is here, we reduce the value with the normalized gradient to come down. And if our weight is here, we increase the value with the normalized gradient to come up. And our goal is to come at that 0 position where there is no gradient to our loss. Okay, so this is our gradient with respect to change in weight, keeping bias as constant. And now this here, same plus sign, sorry for the mistake, this here is our gradient with respect to our biases, keeping the weight as constant. Let me run this, and as we can see, this is our gradient. So for the bias bs, as we have declared before, minus 30 to 30 in range, as you can see from here, for the bias our loss is currently at here. So what should we do? We are at a negative position, so we should increase with the normalized gradient and come up and try to stay at 0. Okay, now this is at 10. So if I increase or decrease it, as you can see, this red dot will move left or right. So let me say I increased it by 2, let's say. Okay, similarly here I increased it by 2 and rerun this. As you can see, we came down a little, and if I decrease this, let's say I made it 8, And similarly here I made it 8. As we are in a negative position, we should decrease the gradient. See, I came up. If I decrease it further, let's say I made it 5, and here also I made it 5. See, I came up more. Similarly, we can adjust this gradient and we can find the optimal position where our gradient is 0. Now, as I have told before, this is only for bias keeping the weight as constant, and the previous one is only for weight keeping the bias as constant. Okay. So what we will do, what we will do is we will plot the 3D curve here, and when we see the 3D curve, let it load. Yeah. See what we can see. This is our gradient slope. Okay. This is the hyperplane I was talking about. This is our gradient slope. In this gradient slope, like this is not that same hyperplane, but this is what we call a hyperplane. In this gradient slope, you can see our optimal point. It should be shifted a little left, where our loss is 0. Okay. See, our loss is almost nearing to 0 here. So what is our bias we can see, and what is our weight we can see from here. Next, we will be seeing that what is the effect of this gradient descent. Let me run this, and now let me explain. As you can see, first what we are doing, we are plotting a range of minus 4000 to 4000 with a step of 100. These are our weights. Say our y is 80, and this is our loss function. ws, this ws, new range of w's weights we are providing, and we are providing our prediction, that is y, the actual y value. Now we are plotting it with all the losses, and we are plotting our weight that we are taking for this much time, that is 1. With 1 weight as red color, you can see it is almost at the least amount of loss possible, but it can be further like improved. So what we are doing here is we are taking our new weight, and we are, as we are negatives, we are reducing with the gradient that we are getting. So what that should give us actually is, that should improve our performance, and then we are plotting it with a yellow color, and as you can see, instead of improving our performance, it is jumping to a higher loss. It is jumping to a higher loss. That should not be the case. But let us see why that is happening. Why this is happening, I will explain you. So this is happening because here, as you can see, what I have told you, if you jump too much, like direction is this, but if you jump too high of a value, you will get to a point that is not your desirable position. So what you need to do, you need to take the direction from gradient, but you need to reduce the value by something called learning rate, so that your descent is slow and steady towards the right direction. For that, what we are doing here, we are introducing a learning rate 1 into e to the power minus 5. That is actually 1 into 10 to the power minus 5. That is very low learning rate. Now we will here with the gradient, we will be multiplying the learning rate, and rerun this, and as you can see now, the y and the red, like this is very, the range is very high. So as you can see, the y is coming close to the red, to a better position. If we print the same thing, if we print the same thing in a lower range of weights, we can see the difference in the values. See, the red point is my current loss at this position with 0.7 being my weight, and this is our new weight at the green. As you can see, it descended a little towards the left, going to the lower loss position. So this is why learning rate is important, and learning rate is actually a hyperparameter that the user declares. So according to your data, how much data you have, you need to declare your learning rate, because see, here the learning rate is 1 into e to the power minus 5. But let's say I did it 1 into e to the power minus 1. That is 1 into 10 to the power minus 1. And then rerun this. You can see my green dot had shooted up a lot. That is the meaning that this is happening. Again, this is happening. We are shooting it up. Instead of going gradually, we are shooting up in the same direction. So this zigzag will happen. So we can't reach our global minima easily. So that is why we keep a right gradient descent. We need to understand the right gradient descent. Maybe I can try minus 4. Yeah, minus 4 gives me a good result. But if I have a larger data set, it is customary, like it is normal to choose a higher, lower learning rate because you have higher amount of data to learn from. Next, we will be coming to our implementation step now. Our implementation. Till now, we were learning what is gradient descent and how we can apply it and how that will be helpful. Now we will be implementing this gradient descent algorithm into our logistic regression that we tried with sklearn. First, we will be splitting the dataset as we are not using sklearn. This is a numpy function to split our dataset into train and validate and test parts. You don't need to worry about this function. This is basic Python and does not have any relationship with our ML except splitting the dataset. If you are not understanding this, you can even use our test train split from sklearn for easier stating. Next up, we can check out the shape of our y trend variable. Yeah. So as you can see, our training we have 8,105 rows. That is more than enough rows for this kind of problem. Next, we will be importing math, that is an inbuilt library in Python, and we will be initializing our parameters. That is first weights and biases we will be randomly initializing. This is the k factor, that is if our dataset is too large, to keep the initialization in a range, we use the k factor. That is man dot square 1 by number of predictors. We are having 3 predictors. That is our maximum temperature T max, minimum temperature T min, and the amount of rain. So the k value is man dot square root 1 by 3. And what this part is doing is, let me explain one by one. First, we will use np.random.seed so that our predictions remain same. If we give the same seed every time, predictions remain same, which helps in debugging. Next, we will be initializing our weights with random values of array size predictions comma 1. So 3, we have 3 predictors. So 3 is to 1 will be our array size. And this random what it does, it chooses a value in between 0 to 1. Now this part what it does is, let's say we have a value between 0 to 1, let's say we got a value of 1. So when we multiply 1 with 2, it becomes 2. Okay, it becomes 2. Now what we are doing, we are multiplying 2 with our k factor. Let's say our k factor is somehow 3. Okay, so 2 with 3, so 6. Now we are we are subtracting with the k factor, that is 3. So 6 minus 3, that is 3. So now what is this doing? Say now similarly our value was 0. Okay, if our value was 0, then my final outcome will be minus 3. So initially my value was between 0 to 1. So this part what it is doing, it is normalizing the value between minus k to k. For us 3 to minus 3 or any value that k is. Next we are initializing our biases with np.ones. Ones means it will make an array of 1 comma 1 dimension with the value 1. And similarly we are normalizing it to our minus k to k range, and we are returning our weights and biases. Okay. Okay, let's initialize this function. Now what is our next function? Next we will be forward pass. Now what is forward pass? Forward pass is we are moving through the function and giving a prediction. So here our y pred equals to x. Our x is an array. multiplied with params. Params is coming from this init param of 0, that is our weight. This at the rate is used for matrix multiplication. So x multiplied with our weights plus our biases. This is nothing but the formula w or m into x plus c. This formula here, this is our y equals to mx plus c, our simple straight line formula, and we are returning our y prediction. Okay, let's run this. Next, what we are doing here, this is our MSE or mean squared error, actual minus predicted whole square, as we have seen this one, y actual minus y predicted whole to the power square. This is our mean square error function that is returning the np dot mean value of our mean squared error, and this is our MSE gradient. For this mean square, now we are calculating the gradient. So what we are returning is actual minus predicted. You will think that our gradient was actually actual minus predicted. Let me write here. Actually, our gradient should be actual minus predicted whole multiplied with 2, right? But here there is no 2, and why that is, like, it is a experimental formula. Why we are not giving this 2? Because after numerous experiments, it is found that if we, instead of straightforward providing the gradient, if we provide gradient divided by 2, it gives better results for our predictions. Nothing else, you can even provide multiplied by 2, but if you provide gradient divided by 2, it provides better predictions. Now that this is done, then we are doing actual minus predicted and returning our gradient. Okay, so that is MSE gradient. Next up, we have our back pass, one of the important parts, where we will be updating our weights and biases. First, what we are doing, we are using the WS grade to get the weight gradient. As we have seen, the weight gradient, as we can see from here, this one, keeping C as constant or the biases as constant, this comes out the value of W grad is actually this loss function, derivative of this loss function. So what is that? 2 multiplied with my y minus y predicted, y predicted multiplied with my x, as C is constant, so multiplied with x. So here also we are doing the same thing. We are taking x transpose and then we are dividing it with x dot shape 0, that is the number of columns we have. This helps in averaging all our gradients so that no big gradient overshoots it. Multiply it with our gradient, that is, let me show you, that is this part is our gradient. Wait this part this part Okay, this much. So our W grade equals to this part without the x is our gradient, and we are multiplying the x value after averaging it. So what we are doing is, let's say we have a matrix. Now we are averaging that matrix with, or you can think of this as, after we multiplied with the gradient, we are dividing all the values with total number of rows and averaging out the gradient values. Next, we are calculating BS gradient equals to NP dot mean, same average mean, NP dot mean, getting the gradient value, and axis equals to 0 means it sums of all the values in that biases array. Next, we are giving parameters 0. We are updating it with our WS grad and multiplying that with our learning rate, as we have seen that is important, or we may overshoot. Similarly, we are updating our biases and multiplying with our learning rate and returning our parameters. So let's run this. Now this is our loop section where we loop through the all these forward and backward passes, and we print our progress. First, we will be declaring the learning rate. Next, we will be declaring number of epochs, means how many times we will be reading the data and upgrading ourselves. Here it is 50,000. You can increase or decrease it according to your data. Next, number of parameters. So we are initializing the parameters using init.params that gives us random weights and biases in a range. We are giving trainx.shape1. What this gives is number of columns in trainx, that is 3, tmax, tmin, and amount of range. Now we are looping through for I in range epoch. We are looping through our 50,000 epochs. First, what we are getting our predictions by using forward pass on, and next we will be getting our gradients for that forward pass. After that, we will be upgrading our parameters for this with this gradient, and next we will be displaying our validation loss for every 10,000 epochs. After every 10,000 epochs, that is, we will find the predictions, we will get the validation loss by using mean squared error, and we will be printing it. Okay, so now finally let's run this and see. As you can see, it started well. Wait one second, I think there is some problem. Let me see for a second. Okay, so I found out the mistake that I made. Let me explain to you. So what we were having previously is we were having our loss equals to YA, that is our YA, we will say Y actual, minus YP, that is our predicted, whole square. Now when we are getting D of L by D of Y predicted, because Y actual is constant, we will get 2 into Y actual minus Y predicted, Y actual minus Y predicted multiplied with D of this one, Y predicted, by D of Y predicted, and this will have a negative sign, as we know. As there is a negative sign, this. Now this will come up to be equals to 2 into Y of A minus Y of predicted multiplied with minus 1. So therefore, if we don't consider the 2, we get Y predicted minus Y actual for our gradient descent. So this is the mistake I have did here. Instead of predicted minus actual, I was passing actual minus predicted. Previously also I have done this mistake. Please look for that. Wherever there is gradient, it will be predicted minus actual and not actual minus predicted. Let me do the mistake and show you what the problem is happening. See, our loss is coming infinity. So that is wrong. Loss cannot, we are increasing the loss instead of decreasing it. So when we do that predicted minus actual, we will get the, sorry, we will get the correct formula, and now our loss will be decreasing. Let's see. As you can see, the loss is decreasing, and finally we got a loss of 22.6 or 22% we can say. So that comes to an end. We have trained our linear regression using gradient descent from scratch, and you can use it like this, and you can save it in a pickle file. All those I will explain later how to do that. and how you can also use you can practice, like you can test this with our test set and get predictions. So thank you for watching the video. Please like, share and subscribe. Thank you.